Right, folks, recording video number 6 in Kinetic Theory of Gases. Today, we're going to discuss about mean free path. If I have to talk about mean free path in itself, then it's not something of a concept that is localized to Kinetic Theory of Gases. Actually, mean free path, a concept in itself, is visible pretty much everywhere. If you are trying to compute the drift velocity in electricity and current, or maybe just trying to find what's the minimum distance a body is going to travel if it's going to collide to other body, mean free path just pops into that point, and instead of treating it as a concept in physics, I would ask you to treat it more of as a problem-solving mechanism in physics, which is visible pretty much everywhere. So, without a further ado, now we're going to dive in and talk about mean free path, and we're going to derive what it means to have a mean free path and how are we supposed to compute mean free path of different molecules in scope of kinetic theory of gases. So let us assume that all these points are like different molecules in free space, and pardon. Okay, and I'm going to draw a cylinder. This is our cylinder, which would play an important role in deriving and learning about the mean free path as a concept in itself. We'll be taking this one big molecule as a reference molecule, and then we'll be deriving how they will interact with all other molecules. But before diving into that, I'm just gonna give you a basic other idea about mean free path. So if this is different molecules in free space, then the definition of mean free path would be if this molecule collides with this one and the second molecule collides with the third one would collide with the fourth one, then the distance would be lambda 1, lambda 2, lambda 3, and say this will collide with the fourth and lambda 4th, right? And the mean free path by the definition itself would be mean equals to lambda plus lambda 2 plus lambda 3 plus lambda 4 by 4, right? Which is the definition of mean free path. And if we just define the mean free path in itself, it is gonna be this distance, the distance that it takes for our one molecule to collide with other molecule before it collide with something else or some other molecule, is basically mean free path in our scenario. Right? Now, coming back to the derivation, and for the cylinder, what we are trying to compute is when especially a particle, as we have defined in postulates of kinetic theory of gases, if you remember, then one of the postulates was in kinetic theory of gases was particles. You can see the first video of this lecture series to get an idea of it. Always travel in straight line. So as we further move into this derivation, what we know at this point is uh, the basic underlying assumption of how we are trying to derive the problem itself. So, in ideal gas, the postulates that we have defined is now visible in these places. So, since we have defined that kinetic theory of gases, the ideal gas always travels in a straight line. The first thing that we did in this problem was we stripped away any possible movement in any random direction, which means the particle has to travel in a direction as defined by us, which will be x-axis, y-axis, or z-axis. And even in that, if we assume that our motion is constrained to say x-axis, then we can just put a cylinder over here, and if the body is if this particle is just going to move in this direction, say in positive x-axis, then we know that the possible collision and the possible collision is just possible when the particle is, say, in between distance of 1 meter, and the collision for the mean free path would be happening only in this box. So, having that idea in the back of your mind, what we will do is, if we define this to be a molecule of diameter d, then let us assume that there are few different molecules and different molecules that we have assumed, right? But right, and when this molecule enters inside the cylinder, we know that this molecule is gonna bump into molecule 1, molecule 2, molecule 3, molecule 4. And we know that it's not going to bump into molecule 5 based on the dimension and full picture that we have drawn here. But we have no idea if it's going to collide with molecule 6th and 7th, right? So, it's going to collide with molecule 6th or 7th if and only if it's gonna if it is like if it has a diameter of d by 2 and the other one having a diameter of d by 2, which implies that if it is perfectly in the center of this cylinder along this axis, then if it moves inside, then it's going to collide with this box, these two molecules, if and only if it is d by 2 inside for 6th and 7th one, right? What does that imply is if we assume for the fact that it is d by 2 inside 6th and 7th molecule, and the molecule itself is of diameter d, then the entire diameter of the cylinder would be itself as 2d. There was no requirement of doing or going through all this pain to end up defining the diameter 2d, but we're just trying to assume a general case scenario, and in general case scenario, the possible conditions would be if the particle is entirely outside, if the particle is entirely inside, and the particle is half inside and half outside, in a case where it might just graze or touch the other particle in a tangential manner, or the particle is half in and half out but has no impact on the particle. So it satisfies the assumption itself that it's traveling in a straight line, and possibly computes and thinks about all the possible scenarios that could be possible in this problem itself, right? Now since we know that the work of the cylinder is to know about possible collisions with our primary molecule, then we can say or assume for the fact that number of molecules in the cylinder um, sorry, then molecules per unit volume in cylinder, oops, cylinder is equals to X. So after that figure, what we are trying to do is, hey, we know that there are these many molecules inside the cylinder, right? But we have no idea how many it is. So instead of assuming a number, what we just did was we just defined it to a variable, and the molecules per unit volume in cylinder, let's say X. Then if we try to compute the mean free path from this point, then um, which is per 1 meter cube would be X, right? So in 2 meters per cube would be 2x, and say if the volume of the cylinder is V meters per cube, then it would be Vx, which gives us the total number of molecules inside the cylinder. No, which gives us the total number of molecules inside the cylinder. Now, to compute the number of molecules, let me check my notes. Yep, inside cylinder would be pi d squared times x times x, which is basically what we did was v times x. If we know that there's in 1 meter cube volume there's x number of molecules, 2 meter cube 2x, then following that logic, if the volume of the cylinder is v, and we have assumed for the fact that diameter of this volume is 2d, then its radius would be d, right? And the height of this or length of this cylinder is 1 meters, then number of molecules inside the cylinder is basically pi r squared h and pi d squared times 1 based on this problem. And x would be x is molecules per unit volume in cylinder, right? Which is number of molecules inside cylinder. Now, what we are interested in is not the number of molecules inside cylinder. What we are interested in is number of collisions in traveling distance. Right? So number of collision in traveling distance, we know that the number of molecules inside cylinder is pi d squared by times x. So number of collision in traveling distance would be also pi d square x collisions in 1 meter distance, which is coming from this place. What this implies is in pi d squared x collisions happens in 1 meter distance, right? So one collision would happen in 1 pi squared by x distance, right? Which is basically the idea of computing mean free path, because we know that the number of collision in traveling distance, that is of 1 meter, if we assume for the fact that the number of molecules inside cylinder is colliding and every other molecule would be colliding, then the number of collision is basically uh, the same distance traveled times the number of molecules that is present in the cylinder, which is pi d squared x, and the distance is again times 1. So with that chain of thought, I hope that this is not confusing you at all. With that chain of thought, what I'm trying to allude to is, okay, if pi d squared x collisions, that is basically all the molecules, is colliding with my particle p, then in 1 meter distance, then one collision would happen in 1 by pi d squared x distance, assuming the fact that the particles in cylinder is uniform, which means we are assuming in this problem that all these particles are uniformly distributed, and the density from point A to point B is the density of particles from point A to point B is uniform, which means we are not assuming that the cylinder has more particles here and less particle density on the other side, or no particle over here. So you should know that. Now, using our ideal gas equation, if we go one step ahead to deduce or to derive this one collision distance, that is mean free path distance, if we use this equation with the ideal gas equation, then what we are trying to do is find mean free path distance, but in terms of PV RT, which is more given in most of the cases while we solve problems. So we know again N by V, if we change the equation, would be N goes V P by RT, where N is number of moles, right? Then X would be N by V times NA, right? And the X is coming from this problem, that is molecules per unit volume in cylinder, which means if N is the number of moles in this equation, PV equals to nRT, then N moles is equivalent to N moles has what one N mole is, basically 1 mole. Say 1 mole would be 6.023 into 10 to the power 23 molecules. So it's basically like we're converting 1 kilograms to grams, which would be 1000 grams. So since this is number of molecules, we don't know how many are there. So this equation itself deduces to, if we are trying to compute the total number of molecules, the total number of moles times Na, which means this gives us the number of molecules present by total volume. right? If n is say, assume 1, then it would be Na by V, right? And this equation itself would be x uh, equals to NV times Na, which is P RT by Na, right? Which would be our second equation. We're sticking to the general equation instead of changing this equation to, instead of using moles like 1 mole, we are sticking to the general equation here because that would be more generalized. So x, which is number of sorry, which is molecules per unit volume in cylinder, in terms of PV PNART would be PRT by Na, and we also know that mean free path distance, free path distance is 1 by pi d squared x, which is one collision distance. Then if we just plug in this value of x here, which would be pi d squared times P and A by RT, and the mean free path distance is pi d squared P and A, which is mean free path distance for one collision, which is the required mean free path distance. Again, to sum up or to summarize, what we are basically doing is, hey, if we assume, if we want to compute the mean free path, that is distance between each consecutive collision, which is usually elastic in this case, then given the postulate that is the particles moves in a straight line and we're constructing the motion in, say, positive x-axis, then assuming that the particles are uniformly distributed in space, right, then molecules per unit volume in cylinder would be x. Again, assumption, if the unit volume is, say, 1 meters cube volume, then the total number of molecules present in that places would be x. 2 meter cube 2x, v meters cube vx, and the number of molecules inside the cylinder again would be same as the volume times molecules present in unit cylinder, which is vx. Vx is basically volume of cylinder pi d squared h, and the pi d squared h assumes the fact that the total number of molecules present in the cylinder would collide with the incoming molecule. So the number of collisions, say in a traveling distance 1 meter, would be basically the total area of that cylinder itself, which is pi d squared times x times 1, which is the distance. So in 1 meter distance, if we have pi d squared x collision, then again unitary method would imply that one collision happened in every 1 by pi d squared x distance. And from ideal gas law equation, if we know that there's n moles of molecules, which is basically, if it is 1 mole, then it's 6 to the power 10 to the power 23 moles, and if it is 0.5, then the number would be given number is in a given volume, which is P by RT. So with that thing in our mind, we can just compute the total number of molecules present in that box, right, which is x that we have defined here in this equations. So we are basically computing the total number of molecules present in any general scenario. And when we plug in the value back in the equation of mean free path, then we are computing the mean free path distance of any two molecules in general space. Assume with the assumption that particles are uniformly distributed, and um, and and there is the motion. The motion is constrained in one direction. So has been a bit of a mouthful again for today, but I hope you get the idea of mean free path, and which is not just applicable in this scenario, but it's more of a generalized concept in itself. Thank you.